Into some word problems using different representations. So, planting trees. Charles and Amy are summer interns at a state park. They are helping to plant trees in an area where there was a forest fire. Charles's uncle owns a tree nursery and is willing to donate a 3-foot tall tree that will grow 1.5 feet per year. Amy goes to another nursery but is only able to get seeds donated. According to the seed package, the trees grow 1.75 feet per year. Charles plants the tree and Amy plants the seed on the same day. Amy thinks that even though her tree will be much shorter than Charles's tree for the first several years, it will eventually be taller because it grows more each year. That makes a lot of sense. It grows an extra 1/4 foot a year. But she does not know how many years it will take for the trees to grow that yard. So will the trees ever be the same size? Yeah, I mean, it definitely seems like this one will pass it. How many years will it take? Well, there's a lot of different ways that we can go ahead and do this. So I'll tell you, I think, the fastest way at the end. So the first thing is the table. So we have the tree and we have the seed. So obviously in both, X is going to be years and Y is going to be height. So this one starts at 3 feet, and then it goes to 4.5, and then it goes to 6, and then 7.5, and then 9, and then 10.5, and then 12. And then I'm going to jump down, I'm going to break down here, and in 12 years, this thing would be 12, 18, 21 feet tall, I think. Okay, the seed is 0, 1.75, and then in year 1 it would be 3.5, and then in year 2 it would be 5.25, in year 3 it would be 7. I don't know if I did this wrong or why am I catching up so quickly? Anyways, in year 4, it would be 8.75. In year 5, it would be 10.5, which I'm almost positive is wrong, so I'm going to pause this real quickly and see where my mistake is. I'm going to find my error. Sorry. It starts at 0, and then it grows in 1.75, so I apologize. So 0, 1.75, 3.5, 5.25. I was saying I caught it way too quickly. So here is 7, etc., 8.75, and then we'll jump down to year 12, and I believe in year 12 it's going to equal 21 feet. So there we go. So there's our table. If we wanted to graph it and write the equation. So the graph, I mean, honestly, I don't want to spend a ton of time with the graph. I hate to sound like that, but the idea would be that if we did graph it, one would start at 3 and it would go up 1.5 a year. The other would start at 0 and it would go up 1.75 a year, and they would meet at 12 years and 21 feet. So that's just sort of a ugly quick of this. I just don't want to spend 5 minutes having you watch me make a graph. And then finally, the equation, I think, is definitely worth looking at. The equation here is y equals 1.5x plus 3, and the equation here is y equals 1.75x. So, hey, if this equals y and this equals y, they must equal each other. So I can set these things equal to each other. And I'll subtract 1.5x, and I'll get 0.25x equals 3 divided by 0.25, and you'll get x is 12 years. And then obviously if you plug it into either this equation or this equation, you'll get 21 feet. So like I said, there's a faster way to do this. What most people do, if they see the faster, is they say, hey, look, this is making up 1/4 foot a year. So it makes up 1 foot in 4 years. So 2 feet in 8 years and 3 feet in 12 years. So that's the faster way to do it. But we've done it with the table, a graph, and an equation. You can see we get the exact same answer, that in 12 years they'll both be 21 feet tall, assuming they keep growing. All right, so explore the meaning of the solution of the planting trees problem by answering these questions. How many solutions does the equation for Charles' tree have? It has infinite solutions. How many solutions does Amy's tree have? It also has infinite solutions, right? Because each of these is its own point, and a half of a year, and at 1 1/4 year, or 1.27 years, etc., right? So, and plus I obviously keep going. So we have all these different answers. In context of planting tree situation, what's the meaning of a solution? A solution is when the trees are the same height, right? Same age and height. That's what we mean by a solution, that they're together. How many xy coordinate pairs are solutions to both Charles and Amy's equations? There's one, right? We know there's one solution because this one keeps going, and now they pass. Like, this one was lower, but now it's higher, and it goes forever. They're never going to touch again in theory. Again. In practice, that might not be the case, but in theory, they'll never catch again. So that brings me to a segue here. When we're going to look at systems of equations, that means that we're looking at more than one equation on a graph at a time. There's really only three things that can happen if we're talking about lines. Once we introduce curves, different rules. But for lines, we can see what we just saw, where they meet once and never touch again. They could be parallel lines where they never touch ever, right? Or it could be the same line twice, which is known as coinciding, where they touch infinitely. And if you think back to some of the equations that we had, especially in 612, we had one where all solutions. Well, that means that the lines were the same line twice, so they always touched. And we had one where there was no solutions. Well, those lines would have been parallel. They would have gone together and never touched and had a solution. All right, so let's go ahead and jump to question 623. It says, 2 of the park rangers also want to help restore the forest after the fire. They plant trees that have been bred to grow as follows. So at year 2, Zeus is 8 feet, Ranger Torres is 6 feet. Year 4, 11 feet, 9 feet. Write an equation for Zeus' tree and for Torres' tree. All right, so Zeus' tree, it looks like it's going 3 feet. So I think the y-intercept would be 5. If I go back, it grows 3 feet every 2 years. So if I go back 2 more years, I'm going to go 3 feet. So it looks like I'm going to get the equation of 1.5x plus 5. Again, if you're wondering why it's 1.5, because it's 3 over 2. And 3 divided by 2 is 1.5. But if I go back to where x is 0, then I get 5. Torres's, if he goes back, he's going 3 feet, so his y-intercept is going to be 3, right? I go back 2 more years, I get to 3, but his rate of growth is still 1.5. So y equals 1.5x plus 3. So it says write an equation for both of these, graph the lines. So if I graph the lines, one starts at 3 and goes up, this is Torres, and one starts at 5 and it goes up 1.5, and this is Zoo. It says, when will Ranger Zoo tree be the same height as Charles's tree? It looks like never, right? They're never gonna touch because they can grow at the exact same rate. They're parallel lines. So you could have answered part B simply by looking at the equation for Zoo and Torres's tree. Explain how you can answer the equation before you graph. Well, we say, hey, look, same slope but different y-intercepts, and that's what parallel lines are. One thing I want to point out to you too is just tying this back into what we were talking about. What if I said, going back to 612, where I said if it's no solution, that means they're parallel. So look, hey, this equation equals y, and this equation equals y, so they must equal each other. So I'm going to set these things equal to each other because they both equal y, so I can do that. And look what happens when I subtract 1.5x from each side. I get 5 equals 3. Does 5 equal 3? No. That's false, right? And I told you, if you get a false answer, they must be parallel in line. If it said 5 equals 5, then we would know that they coincided. All right, 624. In the planting trees problem earlier in this lesson, you wrote equations that were models of an everyday situation. Models are usually not perfect representations, but they're useful for describing everyday behavior and for making predictions. You predicted when the two trees would be the same height. Your linear model made certain assumptions about tree growth. What are some of the assumptions? Well, we assume that it always grows the same all the time. That it's like an even growth. Maybe, if it grew more in spring versus fall, that might not be the case, or whatever. It might have caught it earlier or later in the season, or whatever. We assume they didn't die, etc., etc. What's the appropriate domain and range for the models of growth in Charles and Amy's tree? Well, I think the idea would be Charles's tree. I think was one that started off at 3 feet, right? So when we do that range, I would say it's going to be the range would be greater than or equal to 3 feet. And if he had the seeds, I apologize, but whoever had the tree, it started at 3 feet tall, so the range would be 3 feet or higher. But the domain, it was 0 or more, right? We weren't really concerned about a negative date on those trees. Whereas whichever one had the seed, it started at 0, 0, right? So we would say the domain is greater than or equal to 0, and we would say the range is greater than or equal to 0. I do always get people saying, well, what about, negative, you put it below ground, so shouldn't it have a negative height? No, because we're not measuring its height to the ground. We're measuring its height completely, and that seed still just wasn't a tree with height. I guess if you wanted to measure the seed and say it had height, you could do that, but I'm just trying to answer the question about being below ground. So hopefully that makes sense.